Welcome to Math, Week 16, Logarithms and Properties. This is Module Math-1 on the Math Tutor Self-Study track. This is the final week of the sequence. Today's lesson is 120 minutes. We have 10 practice problems at the end. The week's spine is one idea. Log is the inverse of exponentiation, so log base b of x equals y means b to the y equals x. Plus 3 operational rules, product, quotient, power, and the domain constraint x greater than 0 that you have to respect at every step. Phase A, Math Track. This video is sponsored by Subthesis. Visit subthesis.com to learn more. A logarithm is the inverse of exponentiation. The definition: log base b of x equals y means b to the y equals x. Logs answer the question, what power do I raise the base to in order to get this number? So log base 2 of 8 equals 3, because 2 cubed equals 8. Now the front-loaded call-out for this week, which has to be in your hands before any of the rules make sense. The domain of a logarithm is strictly positive numbers. Log base b of x is defined only for x greater than 0. The reason is structural and follows directly from the definition. The exponential b to the y is always strictly positive. For any positive base b and any real exponent y, b to the y is greater than 0. There is no real y that makes b to the y equal 0. And there is no real y that makes b to the y negative. So when you invert exponentiation, the inputs to the inverse are exactly the outputs of b to the y, positives only. Log base b of 0 has no real value. Log base b of negative 4 has no real value. They are outside the domain. This domain restriction is not a side note. It will dominate the rest of the week. When you solve a logarithmic equation by combining logs and converting to exponential form, the cleared equation may produce candidate solutions that violate the original domain, exactly like the rational equation extraneous solutions trap from week 13. The discipline is the same. Clear the structure, solve, and then verify against the original domain. Any candidate that makes any log argument 0 or negative gets discarded. In code terms, this is also the reason log of 0 is one of the top sources of not a number crashes in machine learning training. The defense, adding a small epsilon, like log of p plus 10 to the negative 8, is the production version of the domain check we are drilling here. Quick agenda: 2 special bases, inverse properties, the 3 core rules, solving exponential equations, change of base, the machine learning connections to log likelihood and cross entropy. A brief you finished Math 1 beat, 10 practice questions, the recap, and a preview of what comes next. Why do logarithms exist? Before we define them formally, let's see where they show up in the real world. The Richter scale measures earthquake magnitude. Each whole number step represents a 10-fold increase in amplitude. So a magnitude 7 earthquake is not slightly stronger than a magnitude 6. It is 10 times stronger. That scaling is logarithmic. Decibels measure sound intensity on a logarithmic scale. A conversation at 60 decibels is not twice as loud as a whisper at 30 decibels. It is 1,000 times more intense. The pH scale in chemistry measures acidity. A pH of 3 is 10 times more acidic than a pH of 4, and 100 times more acidic than a pH of 5. Again, logarithmic. The common thread: when quantities span many orders of magnitude, from tiny to enormous, a logarithmic scale compresses that range into something humans can work with. Logarithms are the mathematical tool that makes these scales possible. 2 special bases dominate the literature. The common log, written log of x with no subscript, is base 10. The natural log, written the natural log of x, is base e. Most machine learning uses natural log because the derivative of the natural log of x equals 1 over x, the cleanest possible derivative. Calculus on log base 10 of x picks up an extra factor of 1 over the natural log of 10, which clutters the algebra. Natural log avoids that. If you see log without a subscript, default to base 10 in finance and engineering contexts, and to base e in machine learning and probability contexts. When in doubt, ask which base is meant. The graph of a logarithmic function is the mirror image of an exponential function, reflected across the line y equals x. On the left, the exponential function b to the x. It passes through the point 0, 1, rises steeply to the right, and approaches 0 as x goes to the left. The x-axis is a horizontal asymptote. On the right, the logarithmic function log base b of x. It passes through the point 1, 0, rises slowly to the right, and drops steeply as x approaches 0 from the right. The y-axis is a vertical asymptote. Key features of the log graph. Domain. X must be greater than 0. Range. All real numbers. The graph passes through 1, 0 because log base b of 1 always equals 0. It passes through b, 1 because log base b of b always equals 1. The graph is always increasing for bases greater than 1, but it grows more and more slowly. The log and exponential curves are perfect reflections because they are inverse functions. Every point a, b on the exponential becomes b, a on the logarithm. 4 inverse properties to internalize. First, log base b of b to the x equals x. Log undoes the exponential. Second, b to the power of log base b of x equals x. The exponential undoes the log. These are the two halves of inverse function. Apply one, then the other, and you get back the original input. Third, log base b of 1 equals 0, because b to the 0 equals 1 for any non-zero base. Fourth, log base b of b equals 1, because b to the first equals b for any base. These 4 show up everywhere. Memorize them. They are how you simplify log expressions on site. 3 core rules turn multiplicative structure into additive structure. Product rule. Log base b of xy equals log base b of x plus log base b of y. Multiplication inside becomes addition outside. Quotient rule. Log base b of x over y equals log base b of x minus log base b of y. Division inside becomes subtraction outside. Power rule. Log base b of x to the k equals k times log base b of x. The exponent comes out as a coefficient. Logs convert multiplication into addition, division into subtraction, and exponentiation into multiplication. This is why logs are useful for any problem where multiplying many numbers would cause precision issues. That is the entire point of log likelihood, which we will see in 2 slides. Let us work through the product rule step by step. The product rule says log base b of x times y equals log base b of x plus log base b of y. Multiplication inside the log becomes addition outside. Example. Expand log base 3 of 9 times 27. Step 1. Apply the product rule. Log base 3 of 9 times 27 equals log base 3 of 9 plus log base 3 of 27. Step 2. Evaluate each term. Log base 3 of 9. Since 3 squared is 9, this equals 2. Log base 3 of 27. Since 3 cubed is 27, this equals 3. Step 3. Add. 2 plus 3 equals 5. Step 4. Verify. 9 times 27 equals 243, and 3 to the 5th equals 243. So log base 3 of 243 equals 5. Confirmed. The key insight. The product rule lets you break a complex log into simpler pieces you can evaluate individually. Now the quotient rule. The quotient rule says log base b of x over y equals log base b of x minus log base b of y. Division inside the log becomes subtraction outside. Example. Simplify log base 2 of 32 over 4. Step 1. Apply the quotient rule. Log base 2 of 32 over 4 equals log base 2 of 32 minus log base 2 of 4. Step 2. Evaluate each term. Log base 2 of 32. Since 2 to the 5th is 32, this equals 5. Log base 2 of 4. Since 2 squared is 4, this equals 2. Step 3. Subtract. 5 minus 2 equals 3. Verify. 32 divided by 4 equals 8, and log base 2 of 8 equals 3, because 2 cubed is 8. Confirmed. Notice the pattern. Anytime you see a fraction inside a log, you can split it into a subtraction of 2 logs. This is the inverse of the product rule, where addition becomes multiplication. The power rule. The power rule says log base b of x to the k equals k times log base b of x. The exponent comes out front as a coefficient. Example. Simplify log base 5 of 125 to the 4th. Step 1. Apply the power rule. Log base 5 of 125 to the 4th equals 4 times log base 5 of 125. Step 2. Evaluate the inner log. Log base 5 of 125. Since 5 cubed is 125, this equals 3. Step 3. Multiply. 4 times 3 equals 12. Verify. 125 to the 4th is 5 to the 12th, so log base 5 of 5 to the 12th equals 12. Confirmed. The power rule is the workhorse of log simplification. Anytime you see an exponent on the argument of a log, pull it out front. Combined with the product and quotient rules, you can break down almost any logarithmic expression. 4 common mistakes to watch for. Mistake 1. The log of a sum trap. Students often write log of x plus y as log x plus log y. This is wrong. The product rule says log of x times y equals log x plus log y. But there is no rule for log of a sum. Log of x plus y cannot be simplified. Mistake 2. The direction error on the power rule. The power rule brings an exponent out as a coefficient. It does not let you pull the base out. Log of x to the k equals k log x, not x log k. The exponent comes out, not the base. Mistake 3. Cancellation errors. Students sometimes think log in the numerator cancels with log in the denominator, but log of x over log of y is not the same as log of x over y. The quotient rule applies when the division is inside one log, not when two separate logs are being divided. Mistake 4. Domain violations. Remember, x must be greater than 0 for log base b of x. When solving logarithmic equations, always check that your answer does not make any log argument 0 or negative. Any candidate that violates this domain gets discarded. When matching bases is impractical, take the log of both sides. Any consistent base works. Usually we pick natural log because the exponential is base e. Worked example: 5e to the 0.2t plus 10 equals 85. Isolate the exponential. Subtract 10 to get 5e to the 0.2t equals 75. Then divide by 5 to get e to the 0.2t equals 15. Apply natural log to both sides. Natural log of e to the 0.2t equals natural log of 15. The left side simplifies via the inverse property to 0.2t, so 0.2t equals natural log of 15. Divide by 0.2. T equals 5 times the natural log of 15. This is the bridge from week 15. Last week you solved exponential equations by matching bases. This week you handle the cases where matching is impractical by taking logs. Now let us solve a logarithmic equation, as opposed to the exponential equations from the previous slide. Example: solve log base 3 of the quantity x plus 2 equals 4. Step 1. Convert from logarithmic to exponential form. Log base 3 of x plus 2 equals 4 means 3 to the 4th equals x plus 2. Step 2. Evaluate the exponential. 3 to the 4th is 81, so 81 equals x plus 2. Step 3. Solve for x. Subtract 2 from both sides. X equals 79. Step 4. Domain check. Plug x equals 79 back into the original log argument. X plus 2 equals 81, which is greater than 0. The domain is satisfied. Final answer: x equals 79. The key technique: convert the log equation to exponential form, solve the resulting algebraic equation, and then verify the solution against the domain. This is the same discipline as the extraneous solutions check from rational equations in week 13. Change of base. The identity: log base b of x equals log base c of x divided by log base c of b for any valid choice of new base c. This is useful when your calculator only does log base 10 and natural log base e, but you need a log in some other base. For example, log base 2 of 7, which no calculator has a direct button for, equals natural log of 7 divided by natural log of 2. Pick whatever base c is convenient. The identity is symmetric in the choice of c. Let us work through a change of base calculation. Example: evaluate log base 7 of 50 using natural log. Step 1. Apply the change of base formula. Log base 7 of 50 equals natural log of 50 divided by natural log of 7. Step 2. Compute each natural log. Natural log of 50 is approximately 3.912. Natural log of 7 is approximately 1.946. Step 3. Divide. 3.912 divided by 1.946 is approximately 2.012. Step 4. Interpret. Log base 7 of 50 is approximately 2.012, which makes sense because 7 squared is 49, which is very close to 50. You could also use log base 10 instead of natural log. Log base 10 of 50 is approximately 1.699, and log base 10 of 7 is approximately 0.845. Dividing those gives the same answer, approximately 2.012. The choice of conversion base does not matter as long as you use the same base in the numerator and denominator. Most machine learning algorithms maximize a likelihood, the probability the model assigns to the observed data. For a dataset of n independent samples, the likelihood is a product of n small numbers. L equals p of x1 times p of x2 and so on times p of xn. If each p of xi is less than 0.01 and n is large, this product underflows to 0 in floating point arithmetic. Your model loss vanishes for purely numerical reasons. So machine learning always works with the log likelihood instead. Log L equals log p of x1 plus log p of x2 and so on plus log p of xn. A sum of log probabilities is numerically stable even for n equals 1 million. The product rule from the 3 core rules slide is what lets you turn the multiplicative form into the additive form without changing what you are optimizing. The cross-entropy loss for classification. L equals negative the sum of yi times log of y hat I. This comes directly from the log likelihood of the model being correct on the training data. The log here uses the same product and quotient rules you just drilled. When you simplify log of softmax for cross-entropy, the algebra cancels beautifully, giving the famously simple gradient y hat minus y. The takeaway: the algebra you mastered this week is the calculus of modern classification. The 16-week journey from -6 to log likelihood is over. Every concept you touched is load-bearing for the math you'll meet in trig, calculus, linear algebra, and statistics. Take a break. The next stop on the math track, Math 3, is trigonometry. It builds on the function and graph intuition you developed here. Now let's check your understanding with a short practice quiz. There are 10 questions. Pause after each prompt to think before I reveal the answer. Question 1. Log base 2 of 8. Choices: A, 2, B, 3, C, 4, D, 8. Pause, then reveal. The correct answer is B, 3. 2 cubed equals 8, so log base 2 of 8 equals 3. The 8 distractor confuses the log with its argument, the read the input trap. Question 2. The natural log of e. Choices: A, 0, B, 1, C, E, D, undefined. Pause, then reveal. The correct answer is B, 1. Log base b of b equals 1 for any base. The 0 distractor confuses log base b of 1 equals 0 with log base b of b equals 1, the swat the special values trap. Question 3. Product rule. Log of xy equals what? Choices: A, log of x times log of y. B, log of x plus log of y. C, log of x divided by log of y. D, log of x to the y. Pause, then reveal. The correct answer is B. Multiplication inside becomes addition outside. The log times log distractor is the multiplicative misread trap, where the multiplication on the inside is mirrored on the outside instead of converted. Question 4. Power rule. Log of x to the k equals what? Choices: A, k times log of x. B, log of kx. C, log of x to the k. D, k divided by log of x. Pause, then reveal. The correct answer is A, k times log of x. The exponent comes out as a coefficient, the exponent out front rule. Choice B confuses an exponent with a coefficient inside the log. C reapplies the exponent outside the log, which is a different operation. Question 5. Free response. Solve log base 2 of x equals 5. Pause to attempt. The answer is 32. Convert to exponential form. X equals 2 to the 5th, which is 32. Domain check. 32 is greater than 0, so it is in the log's domain. Final answer, x equals 32. Question 6. Free response. Expand log of x squared y using log rules. Pause to attempt. The answer is 2 log x plus log y. Apply the product rule first. Log of x squared y equals log of x squared plus log of y. Then the power rule on the first term. Log of x squared equals 2 times log of x. Combine 2 log x plus log y. This is 2 of the 3 core rules from the 3 core rule slide applied in sequence, exactly the algebra that powers cross-entropy simplification. Question 7. Log base a of 1. Choices A, B, 1, C, 0, D, undefined. Pause, then reveal. The correct answer is C, 0. Anything to the 0 power is 1, so a to the 0 equals 1, which means log base a of 1 equals 0. The 1 distractor swaps with log base a of a equals 1. That is the inverse property pair from the inverse properties slide. Question 8. Free response. Solve 5e to the 0.2t plus 10 equals 85. Pause to attempt. The answer is 5 times the natural log of 15. Isolate the exponential. 5e to the 0.2t equals 75. Then e to the 0.2t equals 15. Take natural log of both sides. 0.2t equals natural log of 15. Divide by 0.2. T equals 5 times natural log of 15. Approximate value. Natural log of 15. Approximately 1.946. So t is approximately 9.73. Question 9. Why use log likelihood instead of likelihood in machine learning? Choices. A. Stylistic preference. B. Avoids numerical underflow when multiplying tiny probabilities. C. Faster to compute. D. Required by libraries. Pause, then reveal. The correct answer is B. Multiplying many small probabilities approaches 0, that is, underflow in floating point arithmetic. Taking the log turns the product into a sum, which is numerically stable even for very large datasets. That is the entire reason the field defaults to log likelihood. Reflection 10. How is cross-entropy related to logarithms? Pause to think. Quick recap of Week 16, Logarithms and Properties, with a cumulative review across weeks 13 to 15. Week 16 itself, you converted between logarithmic and exponential forms, applied the product, quotient, and power rules to expand and condense expressions, solved exponential equations using natural log, and connected log likelihood and cross-entropy to the log rules you just drilled. 3 trap families fell: the log of sum trap, writing log of x plus y as log x plus log y; the power rule misapplication, pulling a base out instead of an exponent; and the domain violation trap, accepting candidates that make the log argument non-positive. Cumulative review. Week 13 was rational equations. Clear denominators by multiplying by the least common denominator, then verify each candidate against the original domain to eliminate extraneous roots. Week 14 was radicals and rational exponents. The dual notation, the nth root of x equals x to the 1 over n. The identity, the square root of x squared equals the absolute value of x, and the requirement to verify after squaring, because squaring is many to 1. Week 15 was exponential functions, the shape b to the x, solving by matching bases, and the natural base e, whose self-derivative makes calculus clean. Notice the unifying thread across all 4 weeks. Every one of these topics demands a domain check or verification step because every one involves an operation that is not freely invertible. Division, week 13, squaring, week 14, exponentiation as an inverse target, week 15, and logarithm with x greater than 0, week 16. The common discipline, clear, solve, verify against domain, is the algebraic version of the numerical stability checks you will rely on in machine learning training. Each outcome maps directly forward. Log likelihood is the standard objective for maximum likelihood estimation. Cross-entropy is one log identity applied to softmax probabilities. Numerical stability through log domain arithmetic is the defense against underflow that every classification trainer needs. Logs are how machine learning talks about multiplicative quantities. Coming up next, you have finished intermediate algebra. What is next? Trigonometry, Math 3, and Pre-Calculus, Math 4, prepare you for Calculus 1, Math 5, the first course where every concept reappears in machine learning. Your closed-form regression intuition is now ready to meet the gradients that will carry you through differential calculus, integration, and the chain rule that powers backpropagation. Take a breath. You earned the next stage. That wraps up this week's lesson and the Math-1 sequence. Thanks for watching, and thanks for finishing the course with us. If this helped, please like and subscribe. It tells the algorithm to put this in front of more learners. See you in Math-3. Sponsored by Subthesis, subthesis.com.